All right, hello everyone. This video here, we're going to go through a little bit about field strength, what factors affect the strength of the field, so questions like this where it's like, oh, there's field strength of this, and what's the force on something. Details of that are going to be focused on a little bit more in grade 12 physics, but just a bit of an intro to it. And then we're going to look at designs of electric motors. And so the motor force itself being the big focus in terms of the concepts. So like before, we're going to have a left-hand and right-hand rule that helps you know which way forces would be. And I have some demonstrations of that too. Okay, so this is what I want to start with here. We have a picture of a horseshoe magnet sort of illustrated in three-dimensional perspective here, and a wire going through near it. So we're going to have electrons flowing, actual electrons flowing in a wire, like in reality what's happening. And so we're going to just analyze this and think of like what would happen. Okay, and so our analysis can be based on field lines when we draw them in. So obviously we're going to have field lines going away from north and towards south. And then we're going to have the field line in the electric wire itself. Okay, so I'm going to be trying to illustrate and so on the idea of like the left-hand rule for this would be you stick your thumb in the direction of the electron flow, so kind of into the page here. If you were to point towards your TV screen, computer screen, whatever you're looking at, and then your fingers are curling basically counterclockwise from your perspective here. So what we're going to do is we're going to look for the main idea about opposites attract and likes repel with magnetic fields, and that'll actually help us figure out which way the force would be and why. Okay? It's not new information, really. It's just based on opposites attract and likes repel, basic magnetism stuff. So this is what it looks like. Okay, so you've got your away from north direction, that direction the compass would point. You've got your direction of the magnetic field due to the electron flow itself. If you were to point your thumb in the direction of the electron flow, and then you had your fingers kind of curling in the, right, kind of like this, whatever. I don't know, that's supposed to be a hand. I'm not an artist, but yeah, there's your thumb pointing. I'm looking at my own hand to try and think of which way my fingernails point at least. So electron flow in this way, and then the magnetic north is wrapping this way, right? It's going up on the right and down behind, right? So continue to go down and behind. So that's this right here. That was those arrows there. So you have your magnetic fields that are happening because of A, the magnet, and B, the electron flow in the wire. And so if you look on the left side, we've got likes, which is going to cause a repulsion from that left side. So it's going to push towards the right. And then on the right side, we have opposites. It's going to attract towards the right side. So really, we're going to have a push towards the right. We're going to have likes repel, opposites attract, a push towards the right. So that's really the motor force itself. If we're looking at the end-on diagram, a little easier to visualize, but I mean, it's the exact same diagram based on how I've shown it here, right? Likes repelling, opposites attracting. So the wire has a force to the sideways on it, to the right in this case, due to the magnetic force, the motor force on each of the electrons that are actually going through the wire. So the electrons in the wire are pushed to the right, and as a result, the wire itself is pushed to the right. That's the fundamental analysis just based on magnetic fields that we know about as a fundamental starting point. A nice thing to do, though, instead of having to analyze from such a basic root level, is to have quick, easy hand rules where possible. And so the hand rule for this one is going to be you point your thumb in the direction of electron flow. For electrons, it's your left hand. Thumb in the direction of electron flow, and then your fingers extend out and point in the direction north to south. You'd have to align your hand, orient your hand so that you're looking like this. You're pointing your thumb like this, and then you've got your fingers all stretched out like this, right? And so you've got electron flow this way, and you have your north to south kind of pointing down on the page. So I should use colors here, actually. The north to south is down, and the electron flow is, this way, right? And so if I just rotate this diagram just a touch here, you'll get a little bit more of the idea of the down, north, south, but I don't want the electrons to not point in the right way. So anyways, that's the left-hand rule for this. And then this is the palm of the hand, right? Based on being the left hand, this is your palm. And so the push is out of the page from this picture, but on the picture, it looks kind of like here anyways, but on the diagram above, you could tell it would be to the right. Your hand would push towards the palm, towards the right. Okay, so we've got electron flow, magnetic north to south, push with your palm. Notice that if we consider the exact opposite direction of flow with your right hand, you'd get the same push. Instead of a push out of the page, the perspective here is making it be sort of on an angle, but I mean, realistically, we're just talking about out of the page, and they're just trying to draw it in perspective so you can see the push, or see the vector arrow for it. All right, so the next step here, we're going to look at some demonstrations of this. And so in this one, there's going to be an electron beam. And it's really how old school TVs work. You have electrons flowing from a thermionic emitter, they call it, but basically they heat up and put a voltage on a type of metal in the back that boils off electrons, how they refer to it. Those electrons then are accelerated towards the screen. They travel from the back to the front, and then they get directed side to side and land in a certain spot to paint the picture, basically draw the picture that you see dot by dot. Pretty amazing technology, actually, that they're able to like direct electrons and get them to land exactly where they need to be to make a picture. This is how old school TVs work. So let me just go to beam and magnetic field in my temporary videos here. And here's a little.
I can actually show you that.
So I'm just going to pause here, not pause, but mute here. I'm just going to show, he's just describing that there's, electrons being given off here, and so a beam of electrons is going to travel because some of them get attracted. They get attracted to this plate, and some of them go through a little space, right? So eventually here he turns on the voltage, and there's the beam. So he puts it on for small periods of time because it gives off a little bit of X-rays. But anyways, so the beam there, you'll see, he's describing now the magnetic force stuff. So if you watch the link to this video, he actually predicts the wrong way because he's thinking about traditional current, and then he switches and he says, oh wait, no, we're talking about electrons, so the force is the other way. Because he's just being really traditional and talking about current flow instead of electron flow. So he predicts based on the magnetic hand rule, if you will, or whatever, that the force is going to be up. But then, of course, he brings the magnet in, and if you watch the video and listen to the sound, he's like, oh, wait a minute. Right here's the north. So for us here, we're saying get your left hand out, point your thumb in the direction to the right on the screen, and then your fingers are going to extend kind of into the screen, and your palm of your hand will be facing down, so you have a push down on the electrons, and that's exactly what's happening there. The electrons are getting pushed down by that magnetism coming into play there. And so think of the magnetic field caused by the electrons and the magnetic field caused by the magnet reacting, and you got a repulsion from this side and attraction to that side. That's literally what's causing the force on those electrons. All right. So yeah, you can obviously, there's a link there for that video. You can see it all you want in full, listen to the description, but it's the same as what I'm saying, except he just gets it wrong because he was thinking about flow positives. But then he fixes it and he corrects himself. All good. So I'm going to just type in TV here. So this is a little video I have to show. And so this is a really old, oh boy, not about, this was going to work for me here. Video, I guess. Let me see if I open it with something else. Let's see. There we go. All right, so super old school TV here, crazy, but it's the same idea. You've got electrons getting off the back and they're flying towards the front, and they would be directed to make a picture. Long enough ago in teaching, I've been teaching for a little while here, they quite often the antenna would, when there used to be analog signals in the air, Price is Right would often be on during physics. Okay, see Bob Barker there, Price is Right. And anyways, so I'm going to bring a magnet in. So I'm just going to let myself do the talking here in the video. We got a little electromagnetic force or motor force demonstration for you. So I'm going to old school cathode ray tube television, which is electrodes toward, or electrons, sorry, towards the screen. So I've got electrons traveling. That's going to be the direction of my thumb with my left hand. And then I've got a magnet here, nice strong one. You can tell that that direction, like that, wait, like that, there you go, is the north. So I'm pointing north that way. So I've got the north. So we can predict what will happen here. I've got a north pointing that way. That means the north magnetic field goes around like this, right? So in where the electrons are traveling, the north is pointing that way. They catch that. They got the north coming out here, but then inside the TV, the north is going to be traveling to the left, coming around to the back. Okay. So the electrons, I'll probably show it with my hand in the video here, but the electrons are going to be coming towards, that's your thumb pointing that way. And then you've got the magnetic field to the left, so you're extending your hand to the left. So that means I've got electrons flowing towards you. Yep. I've got the north towards me, towards the left side of your screen, and then the push is going to be up, and so you're going to see the electrons go up. That's the electrons actually, getting pushed up by that motor force, and so they're landing higher than they would have. Okay, so that's the motor force. It's a pretty convincing, like, nice little demonstration. You can predict exactly what's going to happen and so on. And quite a while back, I set up this demonstration just to see if I could, and I was shocked that it worked as well as it does. It's still kind of surprising to me because motors that use motor force, obviously, they are, oh, I forget VLC again, one sec. Hello. There we go. They use many, many wires all wrapped in order to get a substantial effect, right? This is going to be a single wire, this little wire here, just free to roll back and forth on these wires. Okay, so again, I'll let myself explain in the video here. A demonstration of the fundamental motor force, motor principle. Okay, so we've got a little copper wire here. So we're looking for the motor force. There's a magnetic force of repulsion and attraction, right, towards whichever direction I end up saying in the video here, but it's this way. It's on the electrons themselves. And so the electrons are in the wire, and so the wire ends up with a force on it. Kind of crazy. For you to just roll back and forth on those two copper wires. And this is just connected as a circuit. And so we've got a negative terminal coming up to there. So in this copper wire that's free to roll, there's going to be electrons going that way. And the north is the top of this little magnet setup. So we get a north on the top. I have it written on there so I can remember, so I don't have to test each time. Because they're so close together, it's hard to tell which one's the north. So I took them apart more and identified for sure which one's the north. So from the bottom. And so we've got electron flow. I'll just get my left hand in the picture here. Electron flow that way in the rolling wire. I've got a magnetic north facing down, and so there's going to be a push that way. So when I connect the electricity, or turn the switch on the, trying to get both in line here, and then I'll show it close up. But when I turn it on, it goes rushing to that side. And the first time I set this up, I couldn't believe how strong the force there was. You can see that wire getting launched to the right each time I turn that switch on. And then I switch the direction of the wires, and so just not making contact there. I saw it once anyways, but there we go. So you switch direction. Now you're going to have electrons going this way. You're going to have the force, or the magnetic north facing down, and so there's going to be a push towards the camera, if you will. So yeah, this little video here, I'm just going to circular. I don't think it's in the regular videos here. Circular. Type in more words here to get search here. I got too many circular things going on. Yeah. So electron. Pull it up. So this is just not really the best video for showing this, but I'll just describe the idea of how it actually works. So this is same as you saw before, like a beam of electrons, right? But then you put a magnetic field in place to cause a force to the side, and it basically continues to have a force to the side the whole time. And basically, you end up creating like orbital motion, if you will, or circular motion of these electrons. And so the amount of magnetic field strength needed to make this circle, and you can measure the radius and so on, and you can actually measure the mass of an electron. This is how they determine the mass of an electron, by basically being able to determine how much force is needed to make the electron be to travel in a circle, because there's a force needed towards the center, and so you know that force. And so anyways, you can work basically backwards, and eventually where it boils down to F equals ma. You know how much acceleration there is because you know the size of the circle. So a lot of that physics and concepts and relationships there to do with it are talked about in the grade 12 physics course. Do a circular motion, but you can picture how it would come down to F equals ma, and you can actually just like solve for the mass of an electron. So if anybody ever wondered, like, how do they figure out the mass of an electron? That is how they did it. So, excuse me here, just one sec. All right, next up here, we got a demonstration of a little homemade motor that I made. I had a class set of these, and each student would make their own little motor based on the ideas. And so we can analyze very easily how the motor works and the physical design of it, how it makes sense. So that is this right here. Let's press play. All right, here's another design of a basic motor. Got the negative lead this side. This wire goes around and around and around like that, and then back goes the other side. So literally just this wire you see here goes around and around and around and around, and then it eventually comes up here, and I just stripped the green insulation off of the wire, so there's bare copper on each side. And then the wires for the feed just go up and brush against the side. That's the action. So you can see this wire here literally just has a little coil, and then it's stripped and it goes and it just brushes against this. So I'm about to say in the video there, they actually call the portion of this in modern motors, they actually call it the brushes, because they just brush against the wires that are part of the coil. Call them brushes in actual electric motors. And so it's just obviously it is a real motor, but I mean, it's not very functional. We've got, so the difference between this and more functional motors, like mass-produced, more capable motors, is instead of just having one coil of wire, they have multiple coils of wire. And each coil, if I had a version going perpendicular to this, there'd be wires here, right? And so you'd get the electric force causing the motor to turn happening, 4 times per cycle or twice per rotation instead of just the once, right? So it'd be stronger, it'd be more efficient, it'd be more effective. Anyways, let's show you north going that way. And so I've got north going that way. I've got electrons going this way, and so on this side of the coil, I've got to push down. So just catch that there, where we've got on this side, this is the electron flow direction. This is the north, and so the fingers are stretched out this way towards away from north, and so my palm of my hand is facing down, and so there's a force down in all of the electrons running through all of these loops of wire on this side. Reverse the logic, and you're going to have push the other way on the other side, right? So down on this side, up on the other side, and so this motor is going to turn this way when I turn the electricity on. Push down, and so when I turn the electricity on, I can give it a little kick, and it runs in the direction that I described. And I made the magnets closer, and it is not magic, it's just a motor. So that design is this essentially, right? You've got a big old set of loops of wires and so on, and you've got the 2 sides. So if you had a semicircle for contact, you'd have the magnetic force happening for longer, and it would make it a stronger motor. But it works the way it was. So same analysis as before. If you had electrons flowing whichever way, right? So analyze the left side here, electrons flowing into the page. Magnetic north is from left to right. My palm of my hand, when I wish I had a webcam going, I could show you my hand live here. But yeah, force will be up. The other side, it reverses, so it's down, and so you can get this rotation. And so that's the diagram of how this thing works. Another type of motor that I have, so I have a model of it here. A coil of wire like this, and then the connectors, the ends of the wires are there. And so if you picture this wire, this setup here right now, it's easier to think of the coiled conductor magnetic force or magnetic direction. And so we've got electrons flowing out of the battery here, electrons coming in, electrons hitting this, electrons going through this wire, and now it's down and behind, or so up and behind and down in front. So curl your hands of your left hand with your fingers down in front, like closest to you, your thumb automatically aligns to be towards the left. So this is producing a north. So if I connected the power, this north is going to repel that north, and it's going to push away. This south is going to repel that south, and so on. It's going to rotate, right? I can actually take this thing and rotate it. And so you look, okay, and so what's going to happen? We still have north repelling to north. Now we've got north attracting the south. This is all good, right? But then we get to the point where it's like, okay, it stops producing magnetic fields. This is continuing to rotate, and then it hooks back up in the opposite direction, making this a north again, and so on. So this thing just gets a push and a pull, and then another push and a pull, and then another push and a pull, and so on. It just does this. And that's how this motor works. Okay, so we've got the analysis there all mapped out. So this motor here, Model 2, is from a science company, like a science supply company.
So here's another electric motor. You got the negative terminal coming in here. So electrons are flowing. They're going down this.
So you can see this brass piece here
brush
has a semicircle half here and a half there.
Here, hitting against that commutator, you can see it's a split ring commutator. It's half and half. So right now, in this position around here, we've got electrons going around and around like that, which means the left hand would have electrons going around and around like that.
There you go.
And the thumb would point to the left.
So there's the hand rule there. Just touch that.
That's going to be a north over on this end, and south over on this end. The thumb would point to the left. And so like that.
One bit more.
And the thumb would point.
Pause. So electrons going around and around like this in the coil, down in front and up and behind. Thumb is pointing to the left for which direction the magnetic north is. And then,
and so it's going to be a north over on this end. And so that's going to attract to that bar, because this one over here you can see is a south. And then the switch comes, right, where it switches direction, that's going to become a south over on the back end. So it's going to push away. So this thing's going to want to turn clockwise from above. So if I just get contact going here and give it a little flick with my thumb, hopefully I can do this one-handed here. Right, same setup. Just takes two hands.
I had to set up a tripod and splice the videos together here. But yeah, you see it going.
So there it goes.
Right, clockwise from above as predicted. So all good. And that's just, this is a more complicated motor where you have lots of coils, right? In which case you have lots of ends of coils. And so this is the commutator, right? That's the armature, all these different names. This isn't an engineering course about the design of motors, but I mean, just it's a physics course for understanding the physics of motors. But yeah, each of these pairs of coils have a pair of connectors from the ends. So one here and one on the opposite side. So this, you can tell this thing has like, I don't know, 30 or so sets of coils and so on. So it's just way more likely to start on its own when you go and put electricity on, right? Whereas this one, if it was happened to be sitting like this, it wouldn't start on its own. I always have to give it a little kick to get it going, and then it manages to work nicely. So that is that. Okay, so we're going to look at some other types of motors here, little weird designs. And so this simple DC motor, no commutator. So let's go. DC motor, and we use this guy here. It's pretty funny.
What's up, everybody? Welcome back to my laboratory. Safety is #1 priority.
Okay, so let's just jump ahead to where he's showing things here. There we go. So eventually it's got a loop of wire, it's got the contacts, and what you do is you get the contact, you shave off the insulation on one side only, basically, so that it's going to give you a pulse of a push each time. And so you can see this one working. So put the magnet there, and you can just picture like, okay, electrons are flowing, it's making a magnetic north, it's going to be a repulsion. Like, I'm not analyzing this one fully right now, but I don't have a webcam to show you, but you can actually just like, this isn't a trick. Like, you see lots of things, like, I don't know if you've seen the one with the spoons and the coin that spins. Like, that's just hocus pocus. It's not real science. this one is, though. I have a little working model of this that's definitely more finicky to try and make work, so wobbly and whatnot, but it's neat. So you could try to analyze basically it'd be pretty easy if you picture the coil when it is, say, horizontal. It might have, say, electrons flowing this way, and it would make a north. When it's horizontal, it might make a north facing the north here, which is going to cause repulsion, right? So if it's a bit on an angle and that's a north, it's going to cause it to rotate, and so on. Pretty easy to work through an analysis of that one. This one is weirder. Okay, so this is the most simple motor in the world, most simple motor in the world. And so I'll skip ahead to the end result here. So we have a battery, we have a screw, and we have a little neodymium, that's how you say it, magnet on the bottom. And you just brush a wire against it. And the whole thing, this thing will just spin, spin, spin. I do this in class too. But I have this video, so I don't need to make my own, right? But it'll spin, spin, spin. I found it easier if he has the small end here, whichever end that is, the positive or the negative. I do it the other way around, so it has a bigger surface for the screw to spin around on, but you can see it's spinning. So this video was sort of a viral one a little while ago, let's say 10, 15 years ago. And I was in Sudbury at the time with my in-laws, and my brother-in-law is an engineer graduate from U of T in structural engineering. Like he's a big cement guy. We're just analyzing like how it works. In the video, if you watch it, he talks about how it's producing a lot of energy, but it's producing energy, it's converting electrical energy to kinetic energy, it's consuming energy really. Neat video though, if you watch it. I think the link probably still works. But yeah, how does this thing work? So we're analyzing this, and I figured it out eventually. And it was interesting that I was describing like the electrons are flowing this way, and he was hell bent on no, you have to talk about positives flowing, because he's an engineer, and engineers they don't necessarily think about the physics principles as at a root of a level. They're used to just kind of making stuff work, right? But yeah, like I had to sort of talk with him about how, like, seriously, you can talk about electrons flowing or positives flowing, and just use your left hand or your right hand. There are probably some exceptions though, because I'm learning welding. I bought a welder over Christmas, and I'm going to take a welding course, and I know for MIG flux welding, the electrode that you're putting towards the material has to be a positive, and then the ground has to be the ground has to be the positive, and the electrode you're putting towards the metal has to be the negative, and that matters. So I'm guessing there's probably ions that are created, and they have to be attracting or repelling in the right direction. So there are some times where whether it's electron flow or flow of positives really does actually matter, and direction does matter. Anyways, aside from that though, this is the diagram here that helps us understand how this works. Okay, so there's your magnet, and when you brush the wire against, you're going to have current flowing inside of the conductor. The magnet itself is a conductor. Well, obviously, or this wouldn't work, right? And so we're going to have electrons flowing towards the middle. And so from the bottom, it's easy to view here where you have electrons flowing. Am I doing this here? Oh, the way this one was hooked up, actually, with electrons flowing the other way. You can see this is the positive here, so the electrons coming in and going out and so on. This was analyzed based on current. So let's stick with my electron analysis here. It's just logical and easy. I have electrons flowing out. I've got a magnetic north that is up in the direction. So you got you point your thumb to the left and extend your fingers into the page. Your hand now should be aligned so that you're pushing down. Okay, and so the down push converts into a push sideways when you flip this thing right side up, if you will. Okay, so the analysis is that it's going to have a push, a rotational push. Yeah, kind of nifty. Then what do we have here? Oh, let's see this later. The homopolar roller. There's weird things. Let's see if I can get it this quick. Here we go. Just weird designs that actually are real rather than the fake stuff you see so often. But just a AA or even I would deal with a C battery, I think, when I did it. It just gets some magnets on each end, and you just connect a wire across, And again, you're going to get like a force inside of the magnet itself a certain way, and it just can roll across a table. So I've managed to make this one work as well. But again, I have a video of it, so it doesn't really matter whether you see my video or the YouTube video. And again, an analysis is very similar, right? Picture electron flow, I guess, down the page, and you've got your magnetic north a certain direction. You're going to get a push on the electrons forward to make the thing work. So, yeah. So the two current carrying conductors here. If you picture the magnetic fields on these things, you'd have in the middle, we'd have opposites. We have this one's down, this one's up. And so there'd be an attraction between these wires. If you had two current carrying conductors, you could actually have a situation where there'd be an attraction between the wires. So, you know, it's really sensitive, fragile circuitry. You kind of have to engineer based on that, right? Have them like designed so that you're not going to have a force on the wires causing them to like break. So it could be a concern in fine electronics, really, if you have enough current flowing and wires are side by side, there's a real force there. We're looking at this because it actually allows us to just sort of show the idea of how we can talk about field strength and predict amounts of force and so on. And so pretty easy to analyze through here. If you have you know, the amount of current that's flowing obviously is going to be proportional to the magnetic force. Like this, the force is going to be more if you get more current. That's just kind of obvious. We're going to have, so the current in the two wires, right? And then if you had more wire side by side, you know, that's obviously going to lead to more magnetic force. And then if you have the distance between the wires, obviously the further the distance, the less force there's going to be. This could be a direct inverse relationship, or it could be an inverse square, which is common, you know, but basically the farther apart, the less force there's going to be. So you could do an experiment, you could measure forces based on the amount of currents and length and distance between and see if you can determine the relationship. And it literally ends up being this. You can measure the slope of the line you get, right? You get a nice straight line. If this is the relationship, you'll get a straight line. If it was based on inverse square, then you'd have to square the distance and graph that and get a straight line. The slope would be your proportionality constant. Okay, so this is literally how the equation is developed for this. So we end up with this equation for magnetic force. They chose to calibrate this so you have 1 amp of current flowing. You'd have you know, this amount of force. They measured how much force with 1 meter of wire, 1 meter apart, and they calibrated things based on that. And yeah, so you have a formula for magnetic field strength. Again, you can just use these formulas, but it's not a main focus for grade 11. Main idea is the concepts of which direction the forces are. Okay, so that's it for me. I've got students coming into my room here, so I better sign off. So thanks for watching, and like and subscribe, share the wealth. We have other physics students be able to see this stuff as well. So cool, thanks, bye.